Have you ever just stopped and wondered how you move? I mean, you decide to pick something up and your arm just does it. It seems so simple, right? But what's really going on in that split second between the thought and the action? Well, that's exactly what we're going to break down today. This is the incredible story of how your body turns a simple intention into pure physical force.
So let's start with something we all recognize, a simple bicep curl. Whether you're lifting a dumbbell, a bag of groceries, or even just a book, it looks straightforward, but underneath the skin, there is a mind-boggling biological masterpiece of communication and pure mechanics at play.
And that right there is our big question for the day. In that tiny, tiny gap between your brain saying lift and your bicep actually bulging, what on earth is happening? We're about to go on a journey from the big picture world of movement all the way down to the microscopic engines that make it all possible. Okay, so first things first. Every single move you make on purpose starts with a signal. It all begins as a tiny electrical impulse fired from your nervous system, which is basically command central for your entire body.
Here's the basic route that signal takes. Your brain kicks things off with the command, lift. That message then zips down your spinal cord and activates a special kind of nerve cell called a motor neuron. Now, you can think of this motor neuron as the final messenger, the one who carries the order directly to the troops on the ground, your actual muscle fibers. Now, it's worth knowing that your body actually has 3 different kinds of muscle. You've got cardiac muscle, which is your heart. It works all on its own, thankfully. And you have smooth muscle lining your organs, also working behind the scenes. But for our purposes, we are zeroing in on skeletal muscle. This is the voluntary stuff, the muscles attached to your bones that let you walk, run, lift, and, live your life.
To really get how your brain controls all this with such incredible precision, we have to meet the fundamental boots on the ground, the command squad of your muscular system, the motor unit.
So what in the world is a motor unit? It's actually a beautifully simple concept. It's just one single motor neuron plus all of the individual muscle fibers it's connected to. For really delicate movements, like focusing your eyes, a motor unit might have a neuron controlling just a handful of fibers. But for big, powerful movements, like a squat, you'll have motor units where one neuron controls thousands of fibers at once.
And check this out. This visual shows it perfectly. You can see that one motor neuron branching out, kind of like the roots of a tree, connecting to its whole team of muscle fibers. They act as one. When that neuron fires, they all go.
Now, this is where it gets really interesting. Motor units operate under something called the all or none principle. When that motor neuron sends its signal, every single muscle fiber it's attached to contracts with everything it's got. There's no half effort. It is literally all or nothing. So you're probably wondering, how can I pick up a delicate egg with the same muscle I use to lift a heavy box? Well, your brain is smart. It doesn't act like an on-off switch. It acts like a dimmer switch. For the egg, it recruits just a few motor units. For the heavy box, it calls in the cavalry, recruiting tons and tons of motor units to generate more force.
All right, we know how the signal gets to the muscle. Now, let's zoom in, and I mean way in. We're going to go from the whole muscle you can see all the way down to the molecular machinery that actually does the work.
So here we are back at the big picture. We're talking about the over 600 skeletal muscles you have, which by the way make up somewhere around 40 to 50% of your body weight. Pretty amazing, right? Now, let's pick one and dive deeper.
This diagram is fantastic because it shows how muscles are built like Russian nesting dolls. A whole muscle is really a bundle of smaller bundles. Inside the muscle, you have fascicles. Inside those, you have the muscle fibers. And if you go even deeper, inside the fibers, you find these things called myofibrils. And those are built from tiny repeating segments called sarcomeres. And that is the smallest functional unit of your muscle.
Yep, the sarcomere. This little guy is where all the action happens. The entire process, the core of how a muscle actually contracts, is explained by what's called the sliding filament theory.
So how does this microscopic engine actually work? Think of it like a coordinated dance. It starts when that nerve signal arrives and causes a flood of calcium ions to be released. Calcium is basically the key that unlocks the whole machine. Once it's there, it allows 2 protein filaments, the thin one, actin, and the thick one, myosin, to finally interact. The heads on the myosin filament grab onto the actin filament, kind of like tiny little hands, and then they pull. The myosin heads pivot, pulling the actin filaments inward, causing them to slide past each other. This is the sliding and the sliding filament theory, and it's what shortens the whole sarcomere. And of course, none of this happens for free. This whole cycle is powered by ATP, your body's universal energy currency.
Okay, Amazing stuff, right? Let's zoom back out. We've seen how tiny proteins pull on each other at a microscopic level. But how does that translate into the movements we actually perform every day?
First up, you've got concentric contraction. This is what most of us think of when we hear muscle contraction. It's when the muscle generates force and actually gets shorter. So, in our bicep curl example, this is the up phase, lifting the book towards your shoulder.
Next, we have its opposite, the eccentric contraction. This is a bit weird because the muscle is still generating force, it's still under tension, but it's actually getting longer. This happens when you're controlling a load. Think about lowering that book down slowly and with control, instead of just dropping it. Your bicep is acting like a brake system.
And here's a fun pro tip for you. You know that soreness you feel a day or two after a really tough workout? That's called delayed onset muscle soreness, or DOMS. And it's mostly caused by the microscopic damage that happens during these eccentric or lengthening contractions. But hey, don't worry. That damage is actually the signal your body needs to rebuild that muscle even stronger. It's a huge part of how you get stronger over time.
And finally, there's isometric contraction. Iso means same, and metric means length, so same length. Here, your muscle is firing, it's creating tension, but it's not changing length at all. Imagine holding that book steady halfway through the curl. There's force, but there's no movement. All right, let's put this all together and see how these different types of contractions show up in some really common movements.
Let's look at a few examples. When you push off the ground to jump, what's happening in your leg muscles? That's right, concentric contraction. They're shortening to create power. What about when you land and absorb the impact? That's your muscles working eccentrically, lengthening under load to control your landing. And what about holding a rock-solid plank? Your core muscles are firing like crazy, but they aren't moving. That is a pure isometric contraction.
And there you have it. From a simple thought, a brainwave that zips down a nerve, to the release of calcium, the billions of tiny protein filaments sliding past one another, all fueled by ATP, this absolutely incredible, intricate system is happening thousands of times a second, powering every single thing you do.
Every single one of your over 600 skeletal muscles is just packed with these amazing microscopic engines, all waiting for your command. So the only real question left is, now that you know how they work, how are you going to train them?